this week's agenda. I'm planning to start, we'll start chapter 3 today, and hopefully we'll finish chapter 3 as well this week. And then experiment number 2 starting today, right? And it's going to be 2 parts of experiment number 2, hardware and simulation. So for this week, we'll do simulation part first, and then next week we'll do the hardware. Right, and for the hardware, just like the first experiment, I'll do the demo. I'll videotape the demo in the lab and share the video with you, so you can watch next week. Okay, and then this week's assignments, you have homework number 3 due this Friday. Quiz number 3 also this Friday on chapter 3. And then no lab report for this week, but there will be one for next week. Okay, so those are the assignments that are due this week. Homework number 3, quiz number 3, and that will be all. And then no lab report is due this week. Any question on this week's agenda?
Yes, for homework 3, what is the E part in the? Does that just mean exercise, or is that special problems?
Oh, I probably just copy pasted from from a different text from a different, what do you call it, canvas. So yeah, ignore the E. It's just going to be, what is that, like E 2.1 or something like that, or 3 point something?
Yeah, I think it's like E 3.8 or things like
yeah
that.
Ignore the E. Yeah, ignore the E. It's just end of chapter problems. Sorry about that. Yeah, I'll get rid of those. All right.
Thank you.
You're welcome. Thank you. Any other questions? All right, if not, so we finished chapter 2, and then we talked about air gaps, right? Just a little bit of a review on air gap. The reason why it's important for us to learn how to deal with air gap, because this is something that most likely will be inevitable when you are designing or constructing magnetic components such as a transformer or inductor. Just the way cores are being manufactured, they come in pieces, right? So you have to put together 2 pieces into one core. So because of that, then you'll end up with an air gap, right? And then for some applications, you do want to have an air gap, such as a flyback transformer. The reason being, this is one of the topics that one of the equation that we looked at is that energy stored in a energy stored in a core is inversely proportional to mu, right? So the lower the mu, the larger energy that can be stored in a core, right? So how do you lower a mu? How do you lower permeability of the core? Is by introducing air gap, right? Because air gap elongates the BH curve. Basically, you're making the slope of the BH curve to be slower, right? So that means that mu is going to be lower, and then in turn, that would result in a bigger or larger capability of that core to store energy, okay? And so for some applications, such as a flyback transformer, you do want to have an air gap, or not just air gap, you want to have a gap in the core, right? And in the lab, we introduced that physical gap between the 2 pieces of the core by inserting either paper or Kapton tape, right, between the 2 cores, the 2 halves of the core, right? So that's what we talked about last week. One thing that I don't think I mentioned last week that I believe is very important for you to be aware of is that some cores have what they call distributed air gap, right? Means that the gaps are not physically there. I mean, you don't really physically see the air gaps, but they introduce the air gaps within the core itself, within the core material. So when they manufacture the cores, like one solid core, the materials that they used to make this core has air gaps in it, like distributed air gaps. So it's not one physical air gap, but they distribute the air gap all around or all throughout the core, right? So if you can see my screen, right? So I'm gonna maybe Google distributed core. And I see a lot of these on toroid, the toroid core. So distributed air gap. Let's see. Maybe under images. Maybe just air gap without the toroid. I'm looking for maybe some pictures. Maybe this one. Yeah, so you see new ferrites and distributed air gaps, right? So that's something that you might want to consider as well in the future, right? Ferrite core with distributed air gaps, yeah. So here's a picture of a ferrite core, but inside the core, they already introduced the distributed air gap. It will be ideal for a toroid, right? Because if you have a toroid, how do you put together two pieces of half of toroid, right? It's hard to have the bobbins for it. But this one, you can have the bobbins, right? But for a toroid, what kind of bobbin do you use, right? To put together two half of the cores. So for a toroid type of core, it is harder to have a physical air gap. So that's why in the past, I've used toroid cores that have distributed air gaps instead of using a different type of core, right, with a physical air gap like this one right here. Right? Yeah, I wish I could find a picture of the toroid, maybe the one that I have earlier with images. Maybe that's the one that I can find. Let's see. Looks like maybe this one. Yeah, something like this. It's it looks the same as just a standard or typical toroid core, but when you look at the data sheet, it'll say that, or it'll state that the core has a distributed air gap. Okay. Unfortunately, I couldn't find a manufacturer's website that has the toroid core. Yeah. All right, but yeah, that's something that you might want to keep in mind in the future when you are designing an inductor and you want to use a toroid, and then you like to have the inductor with the permeability of the core. If you find out that it's not enough, you need a lower mu to increase the energy storage capability of the core, and you can definitely look for toroid that has distributed air core. Okay. Any question on that one? Okay, that's the one last thing I would like to mention before I move on to chapter 3. All right, no questions. Yeah. Yeah, so you can see there's no E in here. So that's just what do you call it? Copy paste error from a different Canvas class. All right, let's start chapter 3. If you don't have any question on chapter 2, let's start on chapter 3. So chapter 3 is another review, but the focus on this review is more on the magnetic side of the equations, right? It's not going to be like EE410 when I go over in details the different topologies, DC to DC converter topologies. So this is strictly reviewing the different DC to DC converter topologies and focusing more on the magnetic side of the converters, right? So it'll be good review for those of you who took 410 anyways. Okay? So there are many topologies, but most are combinations or variations of the ones discussed in this chapter. Yeah, so there are numerous topologies out there, but the ones that we are going to review in this chapter, these are the basic ones, right? The main ones. And yeah, people came up with variations of these basic topologies. Okay? Each topology has pluses and minuses, advantages and disadvantages. For example, some topologies would impose higher voltage across their components, right? Some others, they distribute the voltage better, right? So then the stress is lower for some topologies. Right? And then some topologies also have the drawback of having discontinuous current at the input as well as the output. Or some topologies would offer benefits of having continuous or smooth input and output currents, right? And that's important in DC to DC application. The reason being, well, that's why we call it DC to DC, right? DC means flat, right? So as much as we could, we want the topology that we use to be able to have a flat DC current at the input and a flat DC current at the output, right? So that's the ideal DC to DC converter. But unfortunately, topologies that we have, most of them, they would not offer those kind of benefits. Right? There's always a trade-off. If you have a topology, if you choose a topology that has good input current, meaning flat DC current at the input, most likely the output will be bad. The output current will be bad, and vice versa. Or if, let's say, you find a topology that provides a good input current as well as output current. When I say good, it means that continuous, right? Flat currents, almost flat currents at the input and output. And there's always a trade-off, that comes with that. For example, it will be more expensive to have that kind of topology, and it means that you will have to use more components, right? So there's always a trade-off. And then we also have isolated topology versus non-isolated topology. And feel free to interrupt anytime. Okay? If anything I say doesn't make sense to you, just interrupt. And then we have this consideration as well when choosing a topology, right? Isolated versus non-isolated topologies, right? Isolated means that the topology has a transformer in it, and the transformer that we use is high switching frequency transformer. Okay, it's not a 60 hertz transformer, but it's hundreds of kilohertz or maybe tens of kilohertz transformer, right? So isolated means there is a transformer in the topology. That means that the input can be isolated from the output, right? And yeah, and then some other topologies don't have that luxury of having isolation between input and output, and that's just going to be non-isolated topologies, such as buck boost and buck boost, right? Those are non-isolated topologies. That means it doesn't have any transformer. It will still have magnetic components, right? Inductors. And then hard switching versus soft switching. There's another consideration that we could look at when choosing topology, right? Hard switching is what we learn in EE433. That's basically PWM, pulse width modulation. Right? That's what we mainly cover in EE433. There's also pulse frequency modulation that you can use. And in EE411, we covered soft switching, right? Which is a different way of controlling how the switch turns on and off, right? So those are, again, different considerations. Soft switching is better when it comes to losses, right? It should, switching losses, I should say, right? It will reduce the amount of switching losses, right? If you use soft switching, but there's always a trade-off, right? Soft switching uses more components and has more complex control in its circuit to control the switches, right? And then another consideration, which is the last bullet right here, is how we can utilize how we would like to utilize transformers in the isolated topology. So if, let's say, you do choose the isolated topology such as flyback, push-pull, full bridge, then one question that you can consider would be what kind of how do we want to use the transformer? How can we effectively use as well as efficiently use the transformer within this topology, right? So that's another consideration that you might think about under isolated topologies. Okay, so you'll see in this. Go ahead.
What does isolated mean, and I guess what does non-isolated mean?
Isolated means it has a transformer, and non-isolated means it doesn't have a transformer.
Got it. Okay, thank you.
Yeah, that's basically what it means. Okay, so that's one last consideration that I have in this list. And in this chapter, we're going to focus on this last bullet, right? And EE410, EE411, as well as this class, we only consider what we call inductor-based DC to DC converters, meaning we use magnetic component as the main energy storage, right? There are other methods for DC to DC converter that don't use inductors. That could be a capacitor, based type of DC to DC converter. That's one topic that I covered in EE527, which is in advanced power electronics. Right? But again, we're going to limit ourselves since this is a magnetic class. We're going to limit ourselves to DC to DC converter topology that make use of inductors as the energy storage, like magnetic components, basically. So choosing the best topology requires a study of input and output voltage ranges, and then current ranges, cost versus performance, size, and weight, right? So yeah, you're gonna have to know all of these first, right? Before you choose a topology, right? We need to know, okay, what kind of input, what kind of output voltage, what kind of input voltage are we dealing with, right? For the DC to DC converter that we're designing, and then what kind of output power, which relates to current, basically, right? Output current that this converter has to provide to the load, right? And then how much is the budget, right? Is it a low cost or high-end, DC to DC converter? That would determine the topology that you choose, right? Size and weight, right, of the converters, that's another thing, right? Would you like the converter to be compact, right? Or would you like the size or the weight of the converter to be light, and so on and so forth, right? So knowing all of these beforehand will be good. The more information you can get, the better it is for you in terms of making the decision of which topology you would like to choose. Okay. Any questions so far? Okay, PWM, I mentioned earlier about PWM, that's pulse width modulation. The two main methods in controlling the switch in DC to DC converter are PWM and PFM. So PWM stands for pulse width modulation, whereas PFM stands for pulse frequency modulation control signals. When the pulse, this is in general what we do, okay? It doesn't have to be this way, but this is typically what we do, is that when we have a switch that we want to control, right? That switch turns on and off. And typically we would send high pulse. Right? So pulse is high to turn on the switch, and we send a low pulse or zero, basically 0 volt to turn off the switch. Right? So that's basically how we control the switch to turn on and on. High pulse for on, low pulse for off. And then the frequency of this pulse, so we are sending, pulse signal into this switch, such as MOSFET. So we send this series of pulses, and then the frequency of this pulse that we are sending into the switch constitutes the switching frequency of the converter, right? So if the pulse that we are using to control the switch to turn on and off happens to have, a frequency of 100 kilohertz, that means that converter is operating at 100 kilohertz switching frequency. Okay. And then there's a common term that we use in DC to DC converter. We call that duty cycle, which is the ratio of the on time, meaning the conduction time of the switch, to the switching period. Switching period is the inverse of switching frequency. Right? So basically T on over T. Right? That's what, I forgot to connect my tablet. So that's basically what a duty cycle is. It's the ratio of T on over T. Right? Any question on that one? While I'm connecting my tablet here. So far, so good?
Can you elaborate on what the switching frequency is?
Yeah, switching frequency is how often we want to turn the switch on and off, right? So it has to be a periodical waveform, right? You want to have a fixed amount of frequency for PWM. I'm talking about PWM right now, to turn on the switch, to turn the switch on and off, right? So that way we could control the output voltage through the switching frequency, right? Through the duty cycle, which involves switching frequency. So that's basically what it is, right? How often do you want to turn the switch on and off? That's switching frequency. So if somebody says, okay, the switching frequency of this DC to DC converter is 100 kilohertz. That means, right, in 1 second, we are turning on the switch, we are turning on and off the switch 100,000 times per second, right? That's how often we're turning on and off the switch, right? Which is, as you can see, that's a lot of actions, right, in 1 second. And these days, it is common to have around 1 megahertz switching frequency. So 1 megahertz means what? We are turning on and off a MOSFET in DC to DC converter 1 million times per second. Can you imagine that? 1 million times per second. To me, that's that's really impressive, right? The technology that you have today. And yeah, there's some converters that can go up to even 4 megahertz. 4 million times per second. We are turning on and off the switch. And this is possible because we are using electronics, right? So electronics is fast rather than mechanical switch, right? I don't think you could do that when you have mechanical switch. But since we are using electronic switch, and that's why we can turn on and off the switch so fast. Right? Does that answer your question?
It does, yeah. And how does that relate to the period, like the switching period?
It's just the inverse, right? So frequency is the period, is the inverse of the period, right? So period, oops, switching, come on.
Oh, I just got it. Okay, yeah. I wanted to ask, like, practically, what does that mean? But it's just a duty cycle.
Yeah, so switching period is the inverse of the frequency, right? So duty cycle relates to, do I have a picture of that? I might, we'll see. Yes, right there, there it is. So if let's say this is the pulse that we send into the switch, then the switching period is from here to here, right? Once the pulse repeats itself, that's one period, right? So that's T of S. Okay, so the inverse of that, the inverse of T of S is called switching frequency. And duty cycle is the ratio of on time. So when the pulse is high, that's when the switch is conducting. When the pulse is off, that's when the switch is off, basically, right? So then duty cycle is the ratio of on time to the switching period, right? And as ideally, switching period is the summation of on time and the off time of the switch. So that's another equation for duty cycle right there. Okay, And sometimes I use D prime to denote the off time. Right? So the on time is related to duty cycle, as you can see. Right? So duty cycle is related to on time, whereas off time, right? So what is the ratio of off time to the switching period? That's going to be 1 minus D, right? Okay, so therefore on time is related to D, off time of the switch is related to 1 minus D. And instead of writing 1 minus D, sometimes I use D prime, right? Which means it's the same as 1 minus D. Any question on this? All right. Now, in general, again, strictly speaking, in terms of inductor-based DC to DC converter, meaning we have magnetic component, whether it be inductor or transformer or both, then the magnetic component, the main energy storage component of the DC to DC converter will have current that would look something like this, right? A triangular waveform, basically. So this is the current waveform on the inductor or transformer of a flyback, right? Or inductor of a buck boost and buck boost. It will look something like this, okay? Triangular waveform. And again, I'm not going to go into the details. If you're interested, and if you're not graduating this year, you can take 410 in the fall. We'll actually go over this in details of why this is a triangular waveform. But for now, just keep in mind that inductor current waveform is going to be a triangular waveform right here, okay? And consists of, as you can see, one period right there, right? And in each period, we see two segments of the current, right? The first one is the charging portion of the inductor current, and then the discharging portion of the inductor current. Keep in mind that inductor is an energy storage component. So we store energy for a fraction of the period, and then we discharge it during the remaining part of the period, right? So charging, discharging, and so on and so forth, right? And this is steady state condition, right? And so again, for those of you who have not taken EE433, or just for now, trust me that the inductor current waveform will look something like this, okay, with respect to time. Okay, and then under ideal conditions, the shape of inductor current in DC to DC converter is triangular waveform, as I said earlier, whose up and down slopes are obtained from this equation right here. This is the equation that we use to describe or to represent these slopes, right? You have a linear slope during charging time, another linear slope in the discharging portion, right? So positive slope, negative slope, positive slope, negative slope, right? And those slopes are being derived from this equation right here that states that voltage across the inductor is equal to L dIL dt, right? So therefore dIL dt, which is the slope of the inductor current, must be equal to VL over L, right? VL is the voltage across the inductor divided by the inductance of that inductor. Okay. Okay, so that's the charging portion, that's the discharging portion, as I said earlier. The charging portion happens when the switch turns on. So anytime the switch turns on, inductor charges, right? And then when we turn off the switch, then inductor discharges, right? So in general, when you have a DC to DC converter, when the switch is on, the supply voltage is connected to the load. So therefore, the supply or the source will deliver the power into the load. And then during the time when the switch is off, we are disconnecting the supply to the load. And so inductor now is the one who's delivering the power to the load. That's why the inductor discharges during the time when the supply is disconnected to the load, disconnected from the load, right? With the upslope occurs when the switch is in the switch in the converter is conducting, the inductor is charging. So from the previous equation right here, right, that dIL dt is equal to VL over L, right? And then we know that if you look at the inductor current, we have again the segment of time when the switch is on, charging, and the other segment of the time when the switch is off or discharging. So this equation now can be broken down into two, right? Charging and discharging. So for charging, right, I'm going to use this subscript on, right? So the slope, dIL dt of the inductor current when the switch is on is equal to voltage across the inductor when the switch is on divided by L, right? Again, that's from the previous equation. And then the other segment is the slope when the switch is off, right? So that's why I call this dIL over dt off, meaning the slope of the inductor current when the switch is off. What is that equal to? That's equal to voltage across the inductor when the switch is off divided by the inductance, right? The same inductance, right? Now the difference between peak and minimum values of the inductor current is what we call inductor current peak-to-peak ripple, or inductor current ripple, or for short, delta IL. So if you look again at this waveform right here, right, you have the minimum value of that inductor current and you have the peak or max value. The difference between the two, right, IL max minus IL min is called delta IL, right, peak-to-peak inductor current ripple. Okay. This value depends mainly on the inductance used per given switching frequency, or if you assume that the inductance is fixed, then we can play around with the switching frequency to adjust peak-to-peak ripple, right? Again, I'm not going to the details of this, but again, in general, right, this peak-to-peak ripple, delta IL, right, is going to be a function of frequency as well as the inductance, right? If let's say that the frequency is fixed, switching frequency is fixed, then delta IL becomes smaller, right? Imagine this delta IL, the difference becomes less and less, or the waveform becomes flatter and flatter if the inductance made bigger, right? So if F is fixed and then L inductance made bigger, then what happens here? Delta IL gets smaller and smaller, right? So the bigger the inductance per given switching frequency, the smaller the delta IL, right? And then likewise, if I assume that inductance now is fixed, inductance is fixed, then if you increase the switching frequency, then delta IL will also go down, right? So the inductor current becomes more and more like a DC, right? And that's important to know, right? Because again, we have DC to DC converter. We want DC current, DC voltage, DC currents, DC voltages inside the converter. So the more flat the waveform is, the better it is, right? Because we want DC within the circuit, okay? Now, there's always a trade-off, as I said, right? If you are using, for example, PWM, and you already have a fixed frequency, right, switching frequency, then if you don't like the delta IL is too big, then one way to do it is to increase inductance, right? So then the question is, why can't we just keep increasing the inductance, right, until delta IL is practically very, small, right, almost zero? So what's wrong with that? Especially for those who have not had EE410. What is wrong with that approach? Why can't we just increase inductance to make delta IL practically zero? What will be the limitation? What will be the practical implication of that? Anybody?
Maybe the physical size of the inductor?
That's correct. That's number one. Physical size of the inductor, right? The bigger the inductance, the bigger the inductor size, right? The size, physical size of the inductor. What else? Besides physical size. What would limit you from making L big as possible?
Material?
Material related, right? Keep in mind that, although we usually don't teach this often in the classes, but cost is also important, right? So cost, budget. At the end of the day, you have to meet a certain budget, right? So bigger inductance is going to be more costly to buy, right? So keep that in mind. Okay, that's kind of the not kind, but those are the limitations. Or those are the reason why we cannot just keep increasing L, right, to minimize the amount of delta IL, right? For practical reasons, right? Number one, the physical size is going to get so big, right? That is going to be just taking up a lot of space, right? If you imagine you have to build it on a protoboard or on a PCB, then imagine the inductance, the inductor is going to be the largest component on the PCB, right? If you make it very big, and then heavy as well, right? Not just big, but also heavy. And then another thing is budget, right? At the end of the day, as I said earlier, right, you have to, when you're designing something, converter, for example, then it has to meet a certain budget, right? So you're limited by the amount of space on a PCB as well as budget. Okay. How about the other one right here? Let's say that I already chose a fixed value of inductance. Why can't I just keep increasing the switching frequency? Why not? What would limit us from doing so? Anybody? I'm expecting people from E410 to know the answers already. So
I'd say maybe there's a time for the MOSFET to turn on and then back off again.
very good. So physical limitation on the switching device. Very good. That's the very first thing, right? That MOSFETs, IGBTs, all of those switching electronic switches, solid state switches. These are all limited when it comes to switching capability, right? They have limitations, right? Yes, theoretically you could do any frequency you want, but unfortunately, when it comes to building the circuit, you're going to have to use a switch, right, to do the turning on and off. And again, these switches have physical limitations, right? They have their own speed when it comes to turning on and off. Okay, so that's the main limitation of why we cannot just increase the switching frequency, right? And there are other things as well, such as anybody from E410 411 can answer. Besides the physical limitation of the switch, what else? Why can't we just keep increasing switching frequency? Come on. People who took 411 especially.
Don't you also have a lot of more heat dissipation if the frequency is higher?
That's correct. So from where? The heat dissipation from where?
Just from switching, so I guess for the FET itself.
That's correct. Very good. That's it. You got it. So from switching losses, right? So when you are using PWM, then the loss equation for PWM is going to be proportional to F, right? So the more the higher the switching frequency, the higher the switching loss, right? So in E411, we talked about ways to reduce switching losses, right? And one of them is through soft switching. Anyhow, those are two main reasons why we cannot just keep increasing switching frequency. Number one, physical limitation of the device. Number two, switching loss is going to get big, right? Again, because of non-idealities of these devices. Okay, very good. Conduction mode, right? So conduction mode in general can be classified into two, and then there's one special case in addition to these two. The first one is called continuous conduction mode, and the second one is discontinuous conduction mode. And then there's a special case, which is the borderline between the two, that's called boundary conduction mode. Continuous conduction mode happens when the inductor current, right here, if I go, do I have a picture of this? Yes, I do, right there. So this is a good picture to show. imagine this is the inductor current in the DC to DC converter, right? Triangular waveform. If that inductor current stays above 0, so this is the 0 level right there. If the inductor current stays above 0 throughout the operating condition of the converter, then that means that converter is operating in CCM, continuous conduction mode. Okay, and then if you keep lowering and lowering the output current, or not output current, sorry, the inductor current. Imagine if I decrease the inductor current, then the triangular waveform is shifting down, right? Shifting down, down, down until this minimum point reaches 0, which is right there, right? So that's the dashed line right here. Right? So that's the case where the minimum of the inductor current touches 0. If that is the case, then the DC to DC converter is reaching its boundary conduction mode. Okay. And then if we even lower the current more, right? So decrease the current more, then what happens is that the inductor current now becomes discontinuous, just like this red one right here, right? Where you have the 0 amp portion of the current, right? So 0 amp, and then charging, discharging, 0 amp again, charging, discharging again, right? So that's the difference, right? And this discontinuity, this 0 segment means that when we discharge the inductor, we discharge the inductor to the point that there is no more energy left in the inductor. That's why it reaches 0, right? And it stays 0, right? There's no more energy left in the inductor until we turn the switch on again, right? Okay, and then we turn off the switch, and then again we fully deplete the energy in the inductor until it reaches 0 and stays at 0, and so on and so forth. If that is the case, then the current that has this discontinuity right there, 0 segments, if the converter has that kind of current, inductor current, then we call that converter operating in DCM, discontinuous conduction mode. Okay. Now, let me erase this. Okay, so per given output power of the DC to DC converter, right? So per given output power, right? So that's given. I could choose different L's, right? I could choose L1, L2, L3, right? Whatever it is. I could choose different values of L, right? For different values of L, you're gonna get different, I'm just gonna use a different page here. For a different value of L, you're gonna get for the same frequency, okay? So given P out min, and then switching frequency. Okay. Let's say that I'm designing a DC to DC converter to output, let's say 100 watts, let's just say. That's gonna be P max, right? P out max. And so P out min is something that you have to determine from the P out max, of course, right? Relative to P out max, where the converter still maintains CCM. So let's say that I want to maintain CCM down to continuous conduction mode, down to, let's say, 10% of 100 watts. So that's going to be 10 watts. That's going to be P out min right there. Okay. So per given P out min value and switching frequency, so per given these values, I could choose L value, right? The inductor that meet those requirements, right? And given L, given the value of L, right? Any value of L, that would give you a different value of delta IL, right? So if you choose 1L, for example, that 1L could give you at 10 watts, it could give you, for example, this much peak-to-peak ripple, let's just say, for L1, right? And then for L2, for example, oh, L2 is actually a bigger inductor, and I could have for 10% of the load, right? I could have this peak-to-peak ripple, okay? Big L, so that's L3, big, or L2, sorry, L2 big. L1 medium, let's call it medium size, right? Or I could pick a small L, right? Small inductance, for which I get bigger peak-to-peak inductor, right? So for the same amount of current there, okay, I could end up with this peak-to-peak voltage ripple, peak-to-peak inductor current ripple. Okay, so this is small L, small. Okay, and then I could pick even smaller L. Let's say that smaller L is orange right here. If that's the case, then I get something like this. Okay, so you can see the trade-off, right, of having smaller to bigger inductance. But what I'm trying to get at is this. I'm going to erase the orange one right there. Just focus on those three cases, right? Now, if I pick the L value at 10 watts at P out mean to be L3, right? You can see that the inductor current touches 0, right? Just like that. This is supposed to be touching, right? That's the 0 amps. Just touches 0. Whereas if I choose L1 and L2, the inductor current, the minimum of the inductor current is always above, right? And what do you call the case when the inductor current touches 0? What mode is that?
BCM?
BCM, boundary conduction mode. Okay, so now I know that if I pick L3, then I am forcing the converter to operate at BCM at 10% of P out max, right, which is the 10 watts. Right? Now this condition right here, right, or this value, I should say, this value of the inductance L3 that I choose right there is what we call critical inductance. Okay, critical inductance. So critical inductance is the inductance value that would produce inductor current that's going to be BCM, right? Borderline, basically. Now, in general, we want our DC to DC converter to operate in CCM. So in general, this is what we want, right? So therefore, it is good for us to know the inductance value at BCM. So L at BCM, which is called critical inductance. It'll be good for us to know this critical inductance value, right? Especially if you want our converter to operate always at CCM down to 10% of the power, for example, right? Why is it useful to know critical inductance? Because if we can calculate that critical inductance, then it'll make it easier for us to choose the inductance value, right? Meaning, if I know LC, then any value larger than LC, right, would give us CCM. You agree with that statement? If if LC, critical inductance, give us boundary conduction mode, that means any value larger than critical inductance will give us CCM. Any question on that statement? Right. So that's called critical inductance. Right here. I have the picture as well, right? So this is called critical inductance. Okay, so inductor in DC to DC converter is selected first based on mainly two design parameters: the peak value, which I have not talked about, and the lowest average inductor current at BCM, which is called critical inductance. Right. Okay. Now, yeah, I forgot about the first item right here, the first bullet. So when you are designing, when you are choosing the inductance value for DC to DC converter, you need to know critical inductance value, which we can calculate. Right? So we need to know LC. That's going to be coming from the lowest operating condition, right? And then there's also the largest operating condition, which is right here. So imagine, remember earlier I used 10 watts as an example, right? So that's P out min, right? If I keep increasing the output power, then this triangular waveform is going to shift up and shifting up, right? And let's say that at max power, P out max equals 100 watts, we have this inductor current, right? So the other design parameter that you have to be concerned with when choosing an inductor is the IL max right here. IL max at P out max, right? So two things there. IL min at P out min, which give us critical inductance, and IL max at P out max, which gives us what? Gives us right here, the peak rating of the inductor, right? So when you buy inductor, right, I know that you learn already from other classes that when you buy an inductor, let's say from DG Key or from any distributor, right, what do you need to know before you buy an inductor? Number one, you need to know the inductance value, right? If you go buy an inductor, you need to know, okay, I want to buy a 10 microhenries inductor, right? You have to know that, right? What's number two? So number two is something that unfortunately not many EE know about, is that when you buying an inductor, you also need to know the peak current of that inductor, right? The saturation current of this inductor, high sat, right? High sat. So that's going to be given in the manufacturer's data sheet, right? So this IL max right there corresponds to the ISAT, right? Saturation current, which has to do with the BH curve. Remember BH curve, right? So this ISAT is sitting perhaps right there, right, for a given inductor. Right? So we want to make sure that when we use this inductor, the current through that inductor does not exceed ISAT, right? Because ISAT means that the inductor is already reaching the knee region of the BH curve. Make sense? Right? So for DC to DC converter, that ISAT is defined to be higher than IL max. So at the very worst condition, meaning maximum output power of DC to DC converter, what is the maximum inductor current? Well, that's IL max right there, right? At 100 watts, for example, what is the maximum current through that inductor? Well, that's this IL max right there, right? So if that is the case, whatever that IL max is, right? When I choose the inductor for this converter, then I want to get an inductor where IL max is less than ISAT, right? So that's two things. Number two. Number one is the LC right here. Well, right here. That's number one, right? So you have to know the inductance, microhenries, and you need to know current when you go buy inductor, okay? Any questions on this? So that's what you need to know next time you buy an inductor, especially for DC to DC converters. Many times I'm some students, doing senior projects and they have not had the EE433 before. They came for my help for sizing inductor. I would say almost all of them, they already know the L value, but they don't really, they're not aware of ISAT. So they just came to me, okay, is 10 microhenries good? Yeah, not just the microhenries, but also the current, right? You need to pay attention to the current because you don't want to saturate that inductor, okay? Especially for, again, for power electronics, for DC to DC converters, you need to know ISAT. Any questions on this? All right. BH loops of magnetics in DC to DC converters. The BH minor loop of magnetic used in DC to DC converters may cover just one quadrant or the entire 4 quadrants. Depends on the topology and conduction mode, right? So we talked about BH loop that can go. Well, actually, I have a picture. I keep drawing it. Yeah, right there, right? So it could be one quadrant. So this is the what do you call it? BH loop, and this is the BH minor loop. So when we operate the magnetic inside the converter, right? There could be just one quadrant operation, such as this one right here. So we just exciting or producing the magnetic in the DC to DC converter that takes up only one quadrant, right? It doesn't go to negative portion of the BH loop. Or I could have a topology, and this is still one quadrant, right? I could have a topology that there you go, that produces a 4 quadrant operation of the magnetic component, right? So it goes positive, negative, right? Voltage wise as well as current. Don't forget that B is proportional to voltage, H is proportional to current, right? So some topologies actually introduces positive, negative voltage and current across the magnetic component. Some other topologies, most topologies, they do it this way, right? Positive change in the component and a negative change in the component, just like the inductor current that we have earlier, right? So positive component, right, from here to here, that's positive change, right? So that's going to be from here to here, that's positive change. And then from the peak back to the minimum, that's a negative change. So that's going to be from here to here. But you can see the current and the voltage stays positive, right? It stays positive. It always above 0. That's why it's, it's taking up only one quadrant for this kind of operation, right? And what is the difference between this one and this one right here? Can you tell? Well, this next one is also one quadrant, but you can see that here, remember, B is proportional to V and H is proportional to I, right? What this implies is that the minor loop touches this axis, the y-axis. It means that I goes to 0. So now I know that a minor loop that is presented by this picture must be coming from DCM, right? Because the DCM is when we have, or BCM as well. So this one is actually BCM because you can see the area is the same as before. If you look at the area of the two, they're the same, right? Okay. So this is DCM or BCM. So that's when you have current, touches 0, right? So that's BCM and that's DCM, right? So if the current touches 0, then the minor loop also touches the y-axis, just like that. Okay. Any questions on this?
How do you know that the current touches 0 in the BH curve?
The current touches 0 because of the DCM right here.
Oh, I guess how did you know that was DCM or BCM then?
H is proportional to I.
Oh,
right?
Okay, got it.
Right? Because I touches 0 right there, right? So this is I of L. This is 0 amps. So if IL is equal to 0, that means H is also equal to 0.
Right. Okay, thank you.
You're welcome. What is the unit of L now? Of H? Ni over L, ampere per turns, right? Ampere turns. How come I forget this? Ni over L per meter.
Amps per meter?
Yeah, amps per meter. There you go. Yeah. All right. So if current is 0, that means H is 0. So that means it touches the y-axis. Okay.
Thank you.
You're welcome. All right. And then another thing is that with CCM and DCM, another point that I have on the previous page, let me erase this, is that imagine if this is the same triangle waveform, right? I'm going to erase this. Assume this is the same triangle waveform, right? So as I increase the power, I shift the triangle waveform up, right? Upward, right? So here is CCM, and here is BCM, right? Okay, now you can see that from the BH curve right here, that for CCM, right, the minor loop travels upward as well, right? Getting so close to the saturation point, right? That if you keep increasing the current, right? If I keep increasing this triangular waveform, right? You gotta watch out, right? Because that's gonna be very close to the saturation point. If you keep increasing again, then what happens? Then it will eventually reach the saturation point. Now the area becomes bigger. Instead of that area right there, now it becomes bigger. And in the time domain, you'll see something like this. So instead of a triangle, you have a larger peak-to-peak current like that, right? What happens if I keep increasing it? Then it's going to be even worse. Now it's going to be in the saturation region. Now what you'll be seeing is this. Okay. And of course, that's dangerous, right? Because this magnetic component is typically connected in series with a switching device. So that switching device is also seeing that current, right? And in the process, it will break that switching device, will melt the MOSFET, you know, because of that big current, okay? So that's why you want to be away from, right? And that's why it's important for us to know ISAT, right? Because that right here corresponds to maybe ISAT, right? Which is, IL max, right? Which has to be less than ISAT of the inductor, of the core. Okay, any questions on this? And this is another example of DCM. You can see it's DCM because it touches 0, right? And yeah, this looks like a transformer instead of a inductor from the bigger area right there. Yeah, we'll see when we talk about the topologies, okay? Whereas inductor is typically a smaller minor loop, just like this one right here. Right? You can see the difference between the two. Right? So smaller area, right, corresponding to delta IL of this inductor current, and then we have a bigger area corresponding to bigger voltage swing across the magnetic component. That could be that's typically encountered in transformer, right? Okay, any questions on that? Well, we'll talk about critical inductance, and we can definitely derive that, and this is how we derive critical inductance. I believe this is what it is, yes. So BL is equal to L DIL dt, as we already know, right? And DIL is equal to BL over L dt, right? So DIL, we can approximate it as delta IL equal to VL over L delta T, right? And what we're looking for is L, right? And if we have, remember that critical inductance is defined from BCM, right? And here's an example of BCM, right? Boundary conduction mode. In BCM, we have a unique situation where the average of the current, this is the average value of the current. We have a fluctuating current, but if we take the average of that current, that average is actually half of the peak to peak, right? So the average current right there, IL average, is actually half of delta IL, right? Or in other words, delta IL is twice the average value. So that's what I have right there, right? 2 times the average value, that's our delta IL, right? Following this derivation right there, the delta IL is 2 times IL average. So 2 times IL average, that bar right there on top of I, that denotes average value. 2 IL average is equal to VL over L times dt. Okay, so I'm looking for L, so I'm going to solve for L. L therefore is equal to VL over 2 times IL average times delta T. And this is again derived at BCM. So therefore our L that we derive in this equation must be LC, critical inductance. Right. Okay, so our critical inductance, as I said earlier, we can actually calculate this. The critical inductance value should be equal to VL over 2 times IL average times delta T. Okay. Now, if a switch on is used, remember we have on and off, right? The pulse that we send to the switch, on, off, and on. Remember, duty cycle is equal to T on over T, right? So therefore, T on is equal to dt, right? So the on time of the switch is equal to dt, whereas T off, the off time of the switch, right? So from here to here, that should be equal to the entire period T minus T on, right? So that's equal to T minus dt, right? That's going to be 1 minus d times T. There you go, right? Any question on that? Okay, so T on is dt, T off is 1 minus d times T. Okay, remember that. T on is dt, T off is 1 minus d times T. All right, so if I use on this equation right here, right? If I use the switch on time, then LC, critical inductance, is equal to VL over 2IL times d delta T, and this, that delta T is actually T on, right? Then T on is equal to dt, right there, right? As I derived earlier, right there, right? And then if I rewrite the equation, then LC critical inductance, now the equation for critical inductance is equal to, if on is used, right, is equal to VL on, voltage across the inductor when the switch is on, times duty cycle divided by 2 times IL average times F, switching frequency. So I just replace T with 1 over F. Okay? And if switch off is used instead of switch on, then the delta T now becomes delta T off, and then VL becomes VL off. See that? It doesn't matter which equation you use, you'll end up with the same values of LC. So at the end, for switch off, the critical inductance value can be calculated from VL off times 1 minus D divided by 2 IL Fs. So this will be the equation that I would use in the following subsections when we derive critical inductance. Okay, either that one or this one. Okay, again, keep in mind that the first equation right there is valid if I use the on time of the switch. The second equation is valid when I use the off time of the switch. Okay. And then we have IL average right there in each of the equation, IL average, right? And that is determined based on the topology that you choose. Different topology will give you different IL average. You'll see. Okay. Transfer function, how do you derive transfer function of a converter? That is something that I go over in EE433. I'm just gonna skip ahead and tell you that, actually it's right here. The transfer function, the easiest way to derive transfer function is by applying volt-second balance, right? Volt-second balance states that the average voltage across the inductor is equal to 0, right? And this should be this should not be new to you, because we know from, or you learn from circuit class, that if you have an inductor, you apply DC voltage across it, right? What's going to happen? what is the voltage across the inductor? Or what happens with the inductor when you apply DC voltage across it? The inductor acts like a what? Like a short, right? For a DC, inductor looks like a short. You agree? For a DC. Well, DC is the same as average value, right? So DC is the same as average value, right? So therefore, the average value of the voltage across the inductor, meaning the DC voltage across the inductor, should be equal to 0, right? Or a short, basically, right? Because you know that the voltage across a short is equal to 0 volt, right? So that's called volt-second balance, right? So I could apply volt-second balance to derive the transfer function of any topology, right? And it goes like this, that, oh, I skip. Yeah, so the very first equation should be this. VL average is equal to VL on, T on, plus VL off, T off, right? So it's always starting from that equation, that VL average is equal to VL on times T on plus VL off times T off. And this has to be equal to 0 for volt-second balance, right? So that's what I have right here, right? VL on, right there, VL on. What is T on? In the previous page, I derived that to be T on is equal to dt, wasn't it? So VL on dt, and then VL off T off, that's VL off T off right there, 1 minus d times T, right, equals to 0. Then when you average it, right, the T cancels, right? So that's why this equation reduces to this equation, right? So right there at the end, you get VL on, VL off, T off equals to 0, and you get this equation right here at the end, because the T cancels, right? T cancels right there. Okay, so that's the equation that we can apply when we look at different topology and we want to derive the transfer function. You just apply this equation. VL average is equal to VL on D plus VL off 1 minus D equals to 0. Very simple, isn't it? Right. Okay, so that's quite hopefully straightforward to use or to apply. And then, yeah, let's just look at this first topology. I only have 5 minutes, I believe. Let's see if I can, maybe. We'll see. Okay, here's a buck converter, right? Now, I didn't draw the ground, but that's the ground right there, right? So a buck converter has a switch at the front end, and then the diode in the middle, and then inductor, and then capacitor, just like that. But again, I'm not going to go into the details of the operation of the converter. That's EE433. But a buck converter means that the output voltage is going to be less than the input voltage, right? Input voltage is going to be lower at the output. It's going to be the input voltage is going to be lowered at the output voltage, right? So power stage is the simplest among all. Main switch is typically MOSFET, and diode is typically a Schottky, right? So that's typically a MOSFET. That's typically a Schottky. If you use another MOSFET there in place of diode, then we call that synchronous buck, right there. Okay. And you can see that in this topology. Remember the trade-off, right? There's so many trade-offs. One of them is that if you look at the input current, it's going to be discontinuous, right? It's not going to be flat. Why not? Well, because there's a switch there, right? Switch turns on and off, on and off. How could you have a flat current, right? If you have a switch in between input and the circuit, right? So that means the input current is going to be a choppy current. In fact, it's going to look something like this. Right? It's never going to be flat. The output current, however, is going to be good because it's connected to inductor. Remember, inductor current looks like a triangular waveform, right? So it's more DC. It's more DC than the input. See, input looks like that, bad, right? This is bad quality. Output is better quality of DC. Okay. Okay, the transfer function. Remember the transfer function for to derive the transfer function, you just need that very last equation using volt-second balance. VL on, T on, oops, sorry, VL on duty cycle plus VL off 1 minus D equals 0, right? So all you need to do in order to derive transfer function is to determine what is the voltage across the inductor when the switch is on, and what is the voltage across the inductor when the switch is off, right? So that should be something that we could do with using circuit analysis, right? So I want to know VL on, because that's what I'm going to plug in into the transfer function equation. What is VL on again? VL on is the voltage across the inductor right there when the switch is on. Switch is on. Imagine the switch is on, assuming ideal. What is the voltage across the inductor? Can you see that? Voltage across the inductor is going to be voltage between this node right there and this node right there, right? So what is the node to the left of the inductor? You can see that's equal to V in, because now we have a short right there, right? What is the voltage at to the right of the inductor? That's going to be equal to V out right there, right? So I know that when the switch is on, voltage across the inductor must be V in minus V out. Anybody disagrees with that? Right? Okay. If you agree with that, then what about when the switch is off? When the switch is off, you can see that the voltage source is disconnected from the load, right? So who's going to supply the power to the load, the energy to the load, right? If the voltage source is being disconnected, then this inductor now is being forced to release its energy. And in the process, it will flip its voltage just like that, right? And it becomes just like a source. So now the inductor is supplying the energy to the load, and in the process, it flips its voltage. And take a look at the diode there. If this is ground, that means 0. And now this is negative on the cathode, right? The cathode is negative. The anode is 0. Which one is more positive, the anode or the cathode? Of course, the anode, right? Even though the anode is at 0 volts, however, the cathode is at negative voltage. So therefore, this diode is going to be forward bias. When the diode is forward bias, that means the diode turns on, right? The diode turns on. Diode turns on right there. It's a short. That's going to pull this node to ground. So this node right now is 0 volt, right there. Right? And what about the right hand side of the inductor? That's going to be V out still. Right? So what is the voltage across the inductor when the switch is off? That's going to be 0 minus V out right there. 0 minus V out means minus V out, right? So then that's it. That's all you need to get in order to derive the transfer function of a buck converter. Transfer function means V out over V in, okay? So let's do that, and then we can adjourn. Right there, volt-second balance, VL on D plus VL off 1 minus D is equal to 0. VL on, we just found out that that's V in minus V out. And then VL off, we just found out that that's minus V out. And just plug in those values, and the rest is just going to be algebra. See that? That's it. It's very simple, right? And at the end, you get the ratio of output over input. Beautiful, right? That output voltage over input voltage equal to duty cycle. That is the transfer function for a buck converter, right? In CCM, ideal, and steady state. So those are the conditions, right? So when the buck converter is already reaching steady state condition and everything's ideal components, and only true for continuous conduction mode, then V out over V in is equal to duty cycle. Very simple transfer function, okay? And I'm going to stop right there.